Look at that, it's 4 o'clock. Hello everybody, it's Friday, day 23, which is it's a large number. Doing well. So we're going to be back with R today, so continuing our kind of preliminary explorations in the foothills of R, to wax lyrical about it. So if you recall, yesterday we really started working with R in to any great degree, and I walked us through a few things fairly slowly. So if we just grab our studio session. So actually, since yesterday, I've done a little bit of tidying some stuff up in my R installation, because I was aware that I had a whole bunch of stuff installed because I've used R on this laptop for analysis since I got the laptop, and it's, I guess probably 2 or 3 years old now, this laptop. I had a lot of packages installed. I had a lot of kind of legacy stuff in R hanging over. So what I've done today is just clean up my R installation a bit, remove a lot of the old packages, and just hope to get to myself to a little bit of a state which is similar to your shiny new R installations. The reason that I want to do that is because I know that there are some packages that we'll install later on where we'll run into problems, and I may have already circumvented those problems. So I wanted to make sure that I encounter them as well, so that we can all solve them together. So hopefully my R installation is now a little bit cleaner than it was. With that in mind, I'll just quickly recap yesterday. We talked yesterday about functions. So we talked about the log function in particular was kind of the function that we initially introduced, just as a way of introducing functions more generally. But we talked about functions. We talked about data types. So we talked about doubles and characters and logicals. So there's examples of those there on lines 16, 17 and 18 now, and how to test for which functions allow you to test for which data type a particular variable is in R. So is double, is character, is logical, and so forth. We also talked about the special data types of infinity, inf, which you can trivially get to by dividing any number by 0. NaN, not a number, which is the result of, for example, subtracting infinity from infinity, gives you not a number. So that's the second special data type, and then Na, which is effectively a missing value. And I've been having fun with missing values today in the bioinformatics that I've been doing. In my regular job. So yeah, missing values can be interesting sometimes. Okay, and then after we talked about data types, we went on to talk about vectors. So vectors are themselves a data type, but they contain instances of the other data types. So a vector has to contain values that are all of the same data type. And if you remember, if we try to, so here we've got a vector of doubles, and here we've got a vector of characters, and a vector of doubles has the data type both the data types double and vector, because it's a vector of doubles. If we try to add multiple data types into a vector, it will change some of those values to a different data type based on this hierarchy here. So character is greater than double is greater than logical. So in the end, everything, quite often everything ends up being a character if we don't know any better. So that was our kind of introduction to vectors. And then we started to look at a few functions of vectors. So seq is a function which allows us to generate vectors, as well as the colon operator, which allows us to make vectors of doubles as well. And then right at the end, we were looking at arithmetic with vectors and how if you add two vectors together, it adds the successive elements together. So here, myvec plus myvec2, actually, let's make sure they're the right thing. Myvec plus myvec2, we end up adding the first elements together to make 7, the second elements together to make 11, and so forth. So that is vector arithmetic. And we also looked at recycling of vectors. So if you do vector arithmetic with vectors of unequal length, then the shorter you end up with a vector that is the result vector is the length of the longest vector, and the shortest vector is recycled to make up your the length of the longest vector. So here we get in our result here, which is length 4 because that's the longest vector in our arithmetic, we get 8 plus 2, 11 plus 3, and then 8 plus 5, and 11 plus 7 because we recycle the shorter vector. Okay, so that's everything that we covered yesterday in a potted nutshell very quickly. And so what I want to move on to today is some slightly more complicated things, mostly with vectors, and then if we get time later on, I want to look at some more complicated data types. And then next week we can start to get more complicated and start to think about introducing packages into the equation to extend the function of R, and we might possibly look at generating graphics and things like that next week as well, just because I think there's going to be a reasonable diversion to undertake relatively early in proceedings. Okay, so we're going to carry on working with vectors today, and we're going to look at a few more functions that we can use with vectors, which will hopefully be quite useful. And then we're going to look at some other things to do with filtering, and that brings us on to relational operators and things like that. So we've got plenty to get through. So we may as well make a start. So what I'm going to do, first of all, I'm just going to shift yesterday's work up off the screen, just so we've got a nice clean slate for today. So we're going to kick in here with day 23. At the moment, you'll notice, although I've been typing everything into a script, what I haven't done is save this script. And I'm not necessarily proposing that I'm going to make this stuff available, because we're not really doing any sort of coherent work in this script. It's just a place for me to type commands as we go so that they stay on the screen if I need them to, basically. But let's actually, before we go any further, let's save this work so that we've got it on the disk. So I'm going to hit my the disk icon in the top of RStudio. That will bring up this file dialog, and I'm going to save my work into my lockdown learning folder. So if you remember, this is the folder which I share with my VM. So just because I'm just keeping everything together, really, but I'm going to save this into my shared folder, and I'm going to put it into week 5 because it is still week 5. So here we go. We're going to put basic _ examples, And RStudio will add the .r extension by default to your script name. So we don't need to worry about adding that, but we can be explicit and say, well, this is an R script, so we're going to call it .r to make sure that we understand that when we come back to it later. If you don't do that, if you just put the name of the file, RStudio will add .r by default because it's like that. So there we go, we've saved it. And now we can hit Control S or Command S whenever we want to keep saving this file to make sure that we keep our commands on the disk. So here now our script editor in RStudio is acting like a souped up text editor for which is specifically kind of written to help us write R. Okay, so as I said, we're going to do some more operations with vectors today. So I'm going to start with some useful functions for vectors. The other bit of housekeeping I'm going to do is I'm just going to empty out my environment. So my environment contains actually a small number of variables because I've restarted R since yesterday, but I want to start with a clean slate. So I'm going to clean my environment. There's a little sweepy brush icon here in my environment pane, which I can press and it will ask me to confirm, are you sure you want to remove all the objects from your environment? So yes, I do, and that empties out my environment. So that can sometimes be quite a useful thing to do, just to stop you getting tripped over. I don't want to get tripped up by variables that already exist in my environment. So there we go. Okay, so off we go. To begin with, I'm just going to create a vector which we're going to use for a few operations. So I'm going to call it X, just because it's easy to type, and I'm going to put a load of doubles in it. So I'm going to make it a vector of doubles. 3, 10, 5. Okay, so this vector has 8 numbers in it. They are all numbers, so we're not going to get any type casting to anything else because they're all doubles. So it's going to remain a vector of doubles. We'll create that, and that then will appear in our environment. You see we've got this vector X, which has a length of 8. It's got 8 values in it in a particular order, so that's useful to see. Just to, partly to show you that if we just look at the contents of it, R takes the values you give it and it stores them in the order you've given them. It doesn't try and rearrange them or anything like that. It just gives you them in the order you've got them. Okay, and I just wanted to use this vector to show you some useful functions that are helpful with vectors. Okay, so vector functions. So I showed you a couple yesterday. Length. So does what it says on the tin, tells you how long a vector is. So our vector has 8 numbers in it, so it's a vector of length 8. Okay, so that's what length does. It tells us tells us how long our vector is, how many elements it has, how many numbers, in this case how many numbers are contained within it. Then we've got unique. So this works a lot like, if you remember at the command line, we used it briefly earlier this week. I'm just going to open my terminal here, actually. Here we go. There's a command line program called Uniq, Uniq, which takes a sorted list of things and gives you back the unique entries. This works in exactly the same way. Uniq will give you back your vector with any duplicate elements removed, basically. So if we run unique over our vector X here, because we have 2 3s in it, we should get back the same vector but with only 1 3 in it. So our duplicate element, which is the 3, has been removed. Incidentally, we can chain functions together. So the results of unique is a vector. Okay, so you give it a vector, and it gives you back another vector. You can pass the vector that results from unique into another method, should you want to. Now there are different ways of doing this, and we might look at different ways of doing this later. The conventional way in what's called base R is to nest your brackets. So if we want to know how many unique elements there are in our vector, we can do length brackets unique brackets x, and this will tell us the length of the vector that results from running unique x. So this should return, oh excuse me, press the wrong button. This should return 7 because we remove the one duplicate element by doing unique. So we remove one of the two 3's, which goes from a vector of length 8 to a vector of length 7. So that's the result. So this is excuse me. This is similar to piping commands together at the command line. You take the output of one command and you use it as the input for the next command. So in this case, the outer command is the thing that comes at the end of the pipe, effectively. There is other ways of doing this in R, but they require us to install other packages, which we're not doing just yet. So for now, I'm going to try and avoid doing this as much as possible, but I just wanted you to know that it was possible to do, that it is possible to chain together commands like this. Okay, which. So which is another thing which a function which works with vectors, and it will tell you, I think numerically, which elements of your vector are obey this logical here. I'm going to come back to this double equals sign here later on. When I'm going to talk about, this is what's called a relational operator, and I'm going to talk about these in a bit more detail later on today. But which will tell this particular function call here will tell me which elements of x, numerically, which elements of x are equal to 3. So if we look at x up here, that is the third element and the fourth, fifth, sixth element. So this should return a vector which contains the entries 4 and 6, because they're my two elements, sorry, 3 and 6, sorry. They're the two elements which are equal to 3. Okay, so that's what this is asking. Which elements of the 8 elements in my vector, which ones are equal to 3? And that is element 3 and element 6. Okay, so that's what which does. Then there's rev. I guess no prizes for guessing what rev does. It reverses your vector. So the rev of x is the same as x, but in the opposite order. So instead of being 6, 4, 3, 8, 1, it's 6, 4, 3, 8, 1, 3, 10, 5. It's 5, 10, 3, 1, 8, 3, 4, 6. So it's the same vector, but the opposite way round. Again, no prizes for guessing what this one does. Sort will sort the elements of your vector by whatever their natural sorting order is. So in our case, we have a vector of doubles, so they will be sorted in numerical order because they're numbers, and that's relatively straightforward. So there you go. That's our sorted vector, because they're now in numerical order. So 1, 3, 3, 4, 5, 6, 8, 10 is our numbers in numerical order. And then we looked at some other operators yesterday. So sum, which will tell you the total. It will add up the total of the numbers in your vector. If your vector isn't numeric, so if it's not a vector of doubles, then I suspect this will fail. So there you go. That's the running total of all of the numbers in our vector. We can find the mean of them. We can find the median of them. We can, I think, is it quantile? What does quantile give you? There you go. That gives you the. So yes, quantile gives you the. There's the median, there's the 50th percentile, and the 75th, the 25th. By default, you can give it, pretty sure you can give it an argument, so you can get the 10th percentile and the 90th percentile and other things out of it as well. And if you want a lot of this all in one go, then you can run the summary. So the summary of this vector will give me the minimum, the maximum, the first and third quartiles, the median and the mean. So it's telling me a kind of a group of summary statistics about my, in this case, numeric vector. So these are all quite useful little functions which we can work with with vectors. Okay, so these all work very well with vectors, and quite often, almost regardless of what you're working with in R, you can in the end summarize it down to a vector in some way, and I'll talk more about that later. But it's usually possible to think of most things in R as a vector, if not everything in R as a vector. So these functions which work with vectors, intelligently applied even across different data structures, can still be really functional. Okay, so so there's some other things which I want to introduce, and I'm aware that this becomes a kind of slew of information, and I'm still trying to take it slow. But there's a load of things which we will come back to use again later, which I want to make sure have been put on the table at this early stage, so that when we come back to them later, hopefully you may not remember everything that I've covered, but at least it will ring some sort of a bell. Okay, so the next thing that I want to talk about is paste, and particularly paste 0. Paste is a way of combining values together. So you can use it to combine vectors together, and if you're bearing in mind, it will recycle vectors as well, so it will work like vector arithmetic, and I'll show you what I mean by that. So if we give paste 0 two values, I'm just going to use my name for this. Paste 0 will take those two values and it will stick them together into a single character. So it'll take, here I've given it two character variables. It will stick those together into one single character variable, like that. Okay, so paste 0 with two values will give me those two values stuck together with nothing in between them. So there's not put a space in or anything like that. If you want to put a space in, then use paste without the 0. And by default, I believe that will put a space between the variables that you give it. So there you go. That's concatenated my two characters together into a single character, but this time it's put a space in the middle. But paste 0 doesn't put the space in, which is quite helpful in a lot of cases, because spaces spaces, as you found in file names and things like that, tend to break stuff. So we tend to use paste 0 a lot, and paste 0 will work very happily with vectors. So if you remember from yesterday, if we do seq 1, 5, we will get the sequence of numbers from 1 to 5. So this is a vector of sequential numbers. We can use paste 0 and I'm just going to use it with a single value. Okay, so the character which is CHR, and then the sequence of 5 numbers from 1 to 5. This will treat this character scalar as a vector of length 1, and it will recycle it 5 times. So this is going to work like vector arithmetic. It's, instead of adding the first element to the first element and then recycling that first element, it will stick them together, and it will use this as a vector of length 1, and it will recycle it 5 times. So to show you what I mean by that, I'm just going to run that command and show you what happens. Okay, so what happens is it takes the CHR and it appends it in front of each of the numbers in my sequence. So I get CHR1 to CHR2, CHR3, CHR4, and CHR5. So it's effectively recycling a vector of length 1 to be able to do that. And this is, again, a relatively useful thing to be able to do, and we will come to circumstances where this is useful, I promise. Okay, so that's paste 0, and the next thing that I want to talk about is how we subset vectors. So if we remember our vector x, so let's get ourselves a clean start here. So subsetting vectors. Okay, up we go. Okay, so we've got our vector x, so let's remind ourselves of our vector x. Okay, there you go. So that's our vector. That vector has 8 elements, and it might be that we want to work with these numbers, but maybe we only want to work with the 5th number. So maybe we're interested in, for whatever reason, we're interested in the 5th number of this vector. So how do we extract that one value from this list of values? And we do that by subsetting the vector, and we subset objects, we subset variables in R using what's called the square bracket notation. So we follow the name of our vector. In this case, our vector is called x. We follow the name of our vector with a square bracket. Okay, and this square bracket is instructing R to subset this object. So in this case, our object is a one-dimensional vector. So it's got a length of 8, and we want to extract one element from it. So, and I said before, we want element 5. Okay, so to extract the 5th element from here, we put a 5 inside the square brackets. And this particular line of code in R will return us the 5th element of our vector called x. Okay, so if we run this, we will get back the value 1, because that is the 5th value of that particular vector. We can subset and get multiple values if we want to. So what about if we wanted the 1st and the 5th element out of this vector? Well, we can do that by, instead of just giving one number, we want to give multiple numbers. And if you're combining multiple numbers in R into a data structure, you do that in a vector. So you have to subset your vector using a vector of numbers. So if you want the 1st and the 5th element, then you have to pass in a vector which has the values 1 and 5 in it. So inside your square brackets, so x is a vector here, and this is a second vector which we're using to subset our first vector. So this particular subsetting operation will give us the 1st and the 5th elements of the vector x. So that is 6 and 1. Okay, so the results of this line of code will be a vector of length 2, which has which has the values 6 and 1 in it. There you go. That is that vector which we predicted we would get out the other end. So we've subsetted our vector which had 8 values in it, and we've just extracted 2 values out of that vector. So this is a useful thing to be able to do in lots of ways, and we will come to much more complicated situations where this is useful at a later date. You could possibly see how you could combine this with the which command that we saw before, which gives you back a list of the elements which equate to a certain value, to extract just those particular values from your vector, for instance. Okay, so there are other ways of extracting elements from vectors. The most useful of these is not to do it numerically. So at the moment, what we're doing is we're saying that we want these particular numerical elements out of our vector. We can do it. There's another way that we can do it, which is by using a vector of logicals of the same length as our vector of interest. So just to illustrate what I mean by that, I'm going to make a vector of logicals which has a length of 8. Okay, so true, false, true, true. That's 4, 5, 6, 7, 8. Okay, so this is a vector of logicals which has 8 elements, all of which are either true or false. So it's a vector of logicals. Okay, so just to confirm that it looks the way we think it looks. There you go. It's a vector of length 8, and it's all of the values are logicals. So if we can check is.logical vec, and it should return true. Okay, so this vector of logicals we can use to filter our vector of doubles, and we do it with the square bracket subsetting notation. So in the square brackets we put our vector of logicals. This has the same length as this vector, so vec has the same length as x. If it didn't, I'm pretty sure it would be recycled, although I would need to check. What this does is this gives us back a vector which is subsetted on the values which are true in our vector of logicals. So where vec is true, we will get that element back from x in our return value for this statement here. For the return value for this, this statement here will contain all of the values of x where vec is true. So vec is true at elements 1, 3, 4, and 8. So they're the values we will get back. So 1 is 6, 3 is 3, 4 is 8, and 8 is 5. So those are the values we will get back. 6, 3, 8, and 5. Okay, so let's run that. There you go. So that vector of logicals has subsetted our vector of numerics. So anywhere that the logical is true, we get that value back out of our double vector of doubles. Now I will show you circumstances in which this is interesting in a second, but in order to do that, I need to talk about relational operators. So we've already seen one of these. So relational operators. The major relational operators in R are equals, meaning equal to, exclamation mark equals, meaning not equal to, greater than, meaning greater than, less than, meaning less than, and then greater than or equal to, and less than or equal to. So these are your major relational operators in R, which allow you to test for apply tests between different values. So let's put some numbers in here and show you how they work. Okay, so the results of these relational operators will be logical values. So if we say 10 equal 10, then R will return true. So 10 is equal to 10. It's a fairly facile statement, but 10 equals 10 is true, and R tells us that. So that's a good test. Okay, 10 equals 9, okay, is false, obviously. This also works for characters as well. So cat is equal to cat is true. Cat is equal to dog is false. Okay, fairly straightforward. That's testing for equivalence. Testing for not equivalence, say the same thing applies. So 10 does not equal 10 is false. 10 does not equal 9 is true. And the same for strings. Cat does not equal cat is false, and cat does not equal dog is true. Okay, so again, relatively straightforward. And then you have these tests of greater than or equal to. So again, I'll just carry on with the same examples. 10 is greater than 10, false. 10 greater than 9, true. Cat greater than cat, false. And this is where R will lie to us. Okay, cat greater than dog, false. No, not true. Okay, so this is because this is testing it's testing our characters on the basis of their alphabetical order, so their alphanumeric ordering. D is greater than C in terms of its alphabetical value. So D is a higher value in the alphabet than C is. So therefore, dog is, in this case, in the case of R, dog is seen to be greater than cat, even though that's not true. Don't at me. Okay, and then the same is true for less than, fairly obviously. 10 is less than 10. No, it isn't. 10 is less than 9. Also not true. Because 10 is greater than 9. We know that because we've already tested it. And I'll not belabor the point, but 10 is greater than or equal to 10. Yes, it is, because it's equal to. 10 is less than or equal to 10. Again, yes, it is, because it's equal to it. So those are our relational operators, generally speaking, and we can apply them to single values like this, but we can also apply them to vectors. So we can test our vector of, so we've got our vector, which is x, and we can apply this logical these relational operators, to that whole vector. So we can say x is less than 5, and this will test every value in x and see whether or not it is less than 5. If the value is less than 5, then this test will return true. If it's greater than 5, greater than or equal to 5, then this test will return false. And therefore we will get the result of this command is to give us a vector of logicals that is the same length as our numeric vector, where each entry in that vector will be the result of the test between the value at that position and 5, whether it's less than 5 or not. So if again we remind ourselves of the contents of x, so for this x is less than 5, for the first value of x, that will evaluate to false. Okay, so 6 is not less than 5, I think we can all agree. Therefore, for the first element of x, this particular test will return false. So in our return value from this statement, the first element of the vector that results will be false. And then we'll get a true and another true and then a false and then another couple of trues and then a couple of falses. But the result will be a vector of length 8, and it will be a logical vector, and it will be the results of that single test, x less than 5, for each of the elements of x. So we're applying this one test across all of the elements of our vector. And so this gives us a vector of the same length as our numeric vector, which is what we need to subset our vector using a vector of logicals. So this test returns a vector of logicals that's the same length as our vector that we might want to subset. So if we want to know not just specific elements of x where we've defined our trues and falses up front, but we want to know which values of x are less than 5, we can do this and this will tell us which ones are, but we can also subset x. And we can subset x by doing x square brackets x less than 5. 5. Because this x less than 5 gives you this vector of logicals, and this vector of logicals will then be used to filter x. So it will return us only the elements of x where x is less than 5. So let's test that. There you go. Everything in there is less than 5. Okay? Which hopefully is makes some sort of sense to you, because this subsetting operation is something that we're going to come back to over and over and over again. As I've already mentioned with chaining methods together, there are more modern, cleaner ways of doing this kind of subsetting, but it's useful to know how to do it in base R before we move on to doing it in any more complicated way. Okay, so so this is testing for x less than 5. We can do any test in here which returns a vector of booleans, so a vector of logicals. So we can apply any of these relational operators. We can apply to the elements of x. So x greater than cat. I don't know what the results of this will be. I think they might be all. It's either going to be all. I think it's all false. Yeah. Okay. So numbers are once they get converted into characters, which they have to be able to do this operation. Numbers sorted alphanumerically, numbers are lower than letters, so the numbers come first. So the statement any number greater than cat is false, because all of the numbers are less than C numerically, they come first. So again, we can filter for that. So filter for all of the values where x is greater than cat. Give us all of the values of x where x is greater than cat, and that will give us no answers. That will give us no values because everything is false. So we end up with an empty set, and that's what this numeric 0 is saying. This is an empty set of values. Okay, so we get nothing back if we do that. We could also say, we did it before, but x where x is equal to 3. There's 2 of those. We know there's 2 of those. But this time, instead of telling us which ones they are, which is what which did, it just gives us back the numbers. So it just gives us back the 3s. So you could use this in conjunction with one of our functions. So how many 3s are there in x? That will tell you how many 3s there are in x. Okay, because that's giving us back. Yes, that's giving us back a vector of length 2 because there are 2 3s in x. There are other operators as well as the standard relational operators. There are also other operators which give you back a vector of logicals. And I just want to highlight one of those at this point because it can be extremely useful. And that is the operator in, which is the word in surrounded by percent signs. So percent in percent, which is a slightly odd looking construct. But this asks, are any of the elements of x in whatever follows it? So are they in this vector of numbers? So 2, 3, 5. So this will give me back a vector of logicals. That vector of logicals will be true for every vector of x that is either 2, 3, or 5, and it will be false for every vector of x which isn't in that set. So it will again be a vector of logicals of length 8. And we can use that vector of logicals, because it's the same length, we can use that vector of logicals for subsetting our vector of doubles. So x in 2, 3, 5, like that, will give us back only the values that are in the set 2, 3, and 5. And we've got 2 3s and a 5 in our original vector, which is still, you can still see up at the top here. Maybe you want all of the even numbers in your set. So we can construct that for this. We can say, okay, so give me x where x is in the sequence from 2 to 10 in increments of 2. So this gives me this seek command here, and if I highlight it, I can just run it on its own. That gives me the set of even numbers between 2 and 10, inclusive. So it's saying, give me the sequence of numbers from 2 to 10, incrementing in 2s. So 2, 4, 6, 8, 10. Okay. So this line here will evaluate to the set of numbers in x which are in the set of even numbers between 2 and 10 inclusive. So 6, 4, 8, and 10 are those from our original. Let's remind ourselves of x. There you go. So you can see they're still in the same order they were here. 6, 4, 8, 10. They've not been sorted into numerical order or anything like that. Okay. We can make this. I'm just going to make this slightly more complicated because I've done this with x because I defined x and I know that it contains numbers between 0 and 10. What if I didn't know what values were in X. If X is some data that I've derived, what if I don't know what numbers are in X, and so I don't know where to begin and end my sequence? So we can do it by saying, okay, let's start at 0 instead, because we're going to assume it's all positive integers. And let's go, instead of going to 10, let's go to the maximum of X. So this will evaluate to the highest number in X, which is 10, okay? And this will give me a sequence going up in 2s from 0 to the maximum value of X. So it will give me the set of even numbers. It will include 0, but it will give me the set of positive integers that are even. And there you go. It will return the same value, but this is then dynamic depending on the contents of X, which can be quite a useful thing to be able to do. Okay, I'm going to look to wrap up now. I've seen a few questions go by in the live chat. So in answer to the question, is it looping through the vector, or does it do it in one operation when it subsets? I'm not actually sure about the internals. You can do these things in loops in R. You could write a loop which did the kind of loops that we were doing in Bash, for A in B, test and return me the logical value. In R, that's much slower than doing this kind of vector comparison. So I suspect that the internals of R are doing something more clever than a loop. But I'm afraid I've never looked at the source code of R. I don't know what the internals are here. I'm pretty sure it's doing it in one operation, but somebody cleverer than me about the internals of R would be able to answer that question. Then 2 questions from Petros about the ordering value. Yes, it does relate to the ASCII values. So I'm pretty sure that numbers are smaller than letters, and I'm not sure which way around it is between uppercase and lowercase. I think that uppercase have higher values than lowercase. So yes, that's true. So lowercase letters have a lower value than higher case letters, uppercase letters, and that is the same ordering as ASCII. So I'm pretty sure it does relate to the ASCII value of these alphanumeric characters. And then finally, can you do modular arithmetic? So that is give me, so modular arithmetic is give me the remainder. So 9 modulo 3. Is it modulo? Is it percent? Yes. So there is no remainder. If you divide 9 by 3, there is no remainder. If you divide 9 by 4, you get 2 remainder 1. So the remainder is 1. So that's your modular arithmetic, I believe. So percent does that in R. So yes, it is possible to do that kind of arithmetic. And if you've ever been asked to solve a problem like the FizzBuzz problem, then this is the modular arithmetic is how you solve that particular problem. Okay, so that's hopefully answered those questions. And it's 5 to 5, so we're going to wrap up for the week. So hopefully that's made, some of that has made some sense to you, and by following along and by doing these operations at the same time and seeing the results, I'm hoping that you're following what we're doing. All of these concepts will be returned to. The reason I'm introducing them now is because we will be using them later when we do more complicated things. So I just want I want everybody to be aware of these concepts and how we use them in R. And then, so then when we come back to them later in slightly more complicated circumstances, hopefully they will ring some bells with you. We've done okay this week. We've done pretty well. We've got through a certain amount of the introductory material. What we're going to do next week, we've got a few more basic, some of these kind of foundational concepts to introduce. We've got a few more of those left to do, but then we're going to start to work with some data. So we'll use some example data to start to show the utility of these foundational elements, yes, we'll start to use this to show you examples of these foundational elements being used in the context of real data sets to do subsetting operations, and we'll look at other things as well. And Petros has refined his question to say use modulo 2 arithmetic to find the even numbers. Yes, absolutely you can. So that's a very good point. So to find the even numbers, instead of doing this that we did before, you could exploit this modular arithmetic. So x equals x modulo, it would be x modulo 2 equals 0. Which would return this would return true for the even numbers. So again, subset x by that, and you would get back the even numbers. So yes, absolutely, Petros, that is absolutely a way that you could solve that particular problem. And again, that would work regardless of the values that were in x. That would return you all of the even numbers in x. Absolutely. Okay. So with that, I will sign off. We'll return on Monday with some more R stuff for you. I hope to see you then. Enjoy your weekend. I'm hoping that the weather in the northeast of the UK, the northeast of England, northeast of England, continues to be as spectacular as it has been all week, because I'm going to enjoy my government mandated outside time if it does. So fingers crossed for that, and fingers crossed for the same where you are. And I will see you next week for more lockdown bioinformatics. So bye everybody. See you next week. Thank you.